All right, let's take a look at section 5.8 and talk about inverse trigonometric functions as they relate to integration. In the previous section, we saw that if we take the derivative of an inverse trig function, we end up with something that's not trigonometric in nature. They're algebraic in nature. For example, you'll recall that if we take the derivative with respect to x of the, let's say the arctangent or the inverse tangent, whichever one you prefer, of u of x, where again u is just a differentiable function of x, then that's equal to u prime over 1 plus u squared. That may have been an unexpected result that the derivative of a arc function, the derivative of an inverse trig function, involved no trigonometry at all. It's simply a rational expression, u prime over 1 plus u squared. Well, note that I can reverse this. If I say the derivative of this is that, well, then the antiderivative of that is this over here. And the same thing will be true for all of our other trig functions, or our other inverse trig functions. Now, you'll also recall that if I have the derivative of the arc cotangent, the arc cofunction of u of x, that's going to equal to almost exactly the same thing, except it's got a minus in front. Okay, so here we can say, okay, the antiderivative of this is this. Well, notice these two are almost exactly the same, except this has a -1 constant being multiplied in. If I multiply this by -1, it would give me that. So because of that, I could just say, well, that -1 constant, let me just factor that out. After all, differentiation and integration are linear operations. Negative constant, or really any constant, can be factored out. We can work on this, and then we can put the negative back in at the end. So here, we don't need two separate functions to speak about these kinds of expressions. So when we look at these, we don't see these as two separate functions. We see them as one function and the negative of that function. So when we take the antiderivatives of these, we're not going to consider these separately. We're going to say, okay, if it's positive, well, then it's the arctangent. If it's negative, well, then it's just negative arctangent. We're not going to bother with the cotangent at all. As such, even though we have 6 arc functions, we're only really going to be dealing with 3 of them. So we have a theorem which summarizes our results. Let u of x be a differentiable function obviously a function of x. Right? Let u of x be a differentiable function of x. And here we're going to consider a constant. We're going to call it a. And the only restriction on a is it should be positive. Differential function. And let a be a constant that is greater than 0. We want it to be positive. Assuming that you have a differentiable function of x and a positive constant, then the antiderivative of du over the square root of a squared minus u squared is equal to the arc sine, or the inverse sine, whichever notation you prefer, of u over a plus the typical constant of integration that you're used to. The integral of du over a squared plus u squared is equal to 1 over a times the arctangent of u over a, plus, again, your constant, and the integral of du over u square root of u squared minus a squared. That's going to equal to 1 over a times the arc secant of the absolute value of u over a plus a constant of integration. All right. Note that we don't bother with any of the cofunctions, because if we want to find the integral of this, okay, that's the arc sine. If I want to find the integral of the negative of this, well, I could now talk about it in terms of the arc cosine, or I just stick a negative on the outside of that and be done with it. Same thing here. I could either talk about this integral in terms of arctangent and the integral of the negative of this in terms of arccotangent, or I could just say, well, the positive one is arctangent and the negative one is negative times the arctangent, or negative 1 times the arctangent. So here we don't bother with the cofunctions. We say, oh, if we need a negative, we'll just stick a negative on at the end, like that. We can show that these are true by simply taking the derivative of both sides of this. So here, let me pick on the second one. Proof of this, or at least proof of the second one. Incidentally, the proof of this one, I believe, or maybe it's this one. The proof of one of these is in the assignment, in the homework and such. So here I'm going to just prove this middle one. I forget which of these it is. But in any event, let's just start with this. Let me take this and take its derivative. So let's find the derivative with respect to x of 1 over a times the arctangent of u over a plus a constant. Okay, well, let's see. Differentiation is a linear operation, which means here I can split this. So I can write this as dx of 1 over a times the arctangent of u over a plus dx, the derivative of the constant c. And again, since differentiation is a linear operation, this constant can be factored out. And so we can write this as 1 over a times dx of the arctangent of u over a plus the derivative with respect to x of the constant c. Okay. Well, now we know the derivative of a constant must equal to 0. Going back to basic differentiation, we know that the derivative of any constant must be 0. Okay. Now this is not a basic differentiation, but it's one that we saw in a previous section. And the derivative of the arctangent is going to be the derivative of this expression divided by 1 plus the square of this expression. So here, let me write it this way. I'm going to take the derivative of that expression. Now keep in mind, u is a function of x. So here, this is not constant, over 1 plus the square of that expression. So that's going to be 1 over a. The derivative with respect to x of u over a, well, remember, u is a function. So to take its derivative, it's just u prime over a over, if we're squaring this, that's going to be 1 plus u squared over a squared. Notice here, I can give these a common denominator by multiplying. Instead of writing this as 1, I can write that as a squared over a squared. And now since they have a common denominator, I can add them. So this is going to be 1 over a times u prime over a over, and now that's going to be a squared plus u squared over a squared. Let's see here. I'm going to a squared plus u squared over a squared. Just like that. Okay. Now here I'm dividing by a fraction, which is the same as multiplying by the reciprocal of the fraction. So I can write that as 1 over a times u prime over a times a squared over, let's see, a squared plus u squared. And here, a times a is a squared. So these divide this. And we're left with u prime over a squared plus u squared. Okay, so the derivative of all of this is equal to that right there. So dx of 1 over a times the arctangent of u over a plus some constant is equal to, all of this stuff right here, is equal to u prime over a squared plus u squared. Okay, so now let me go ahead and take the integral of both sides with respect to x. Here it's acceptable to take an integral with respect to x because after all, u is a function of x. Just like that. Okay, so, well, that's u prime dx. If you think back to Cal 1, what is that? U prime dx. The derivative of a function times the differential of the variable of that function. Anyone remember that? That's a differential. That's du. So here we can write this as integral of du over a squared plus u squared. So integral of du over a squared plus u squared is equal to, and now we have the antiderivative of the derivative of our expression with respect to x. Or, if you want to write it this way, you can even write that as the integral of the differential of all of this expression here. But by the fundamental theorem of calculus, that just gives us our original expression here. So here that's going to be the antiderivative of the derivative gives us just this function. So that's going to be 1 over a arctangent of u over a plus some constant, which is, of course, a typical constant of integration that we usually use. So here, that concludes our result. That shows that the integral of du over a squared plus u squared, that's here, is equal to 1 over a times the arctangent of u over a plus the typical constant of integration. And that makes us happy. The other proofs are pretty much similar. And in fact, one of these two is going to be in the homework. I forget which one. I'm pretty sure it's the first one, though. So let's take a look now at some examples of using these. All right, so for our first example, we're going to integrate 12 over 1 plus 9x squared. Okay? All right. A big part of integrating is pattern recognition. What does that look like? Well, it looks most like this one, because this is the only one that doesn't have a square root anywhere in the integrand. So I think it's going to be this one. I say, well, what do you mean you think? It's the only one without a square root, right? Well, sometimes looks can be misleading. Every once in a while, you're going to see something that looks like it should be one of them when really it should be the other. But my best guess is it's this middle one, and if it's not, well, I'll find out soon enough. Right? I'll try it, and I won't be able to make it work. So here, I think it's this one, because I have du over a squared plus u squared, constant squared plus variable squared. Constant squared, that is 1 squared, plus variable squared. There's a 12 here that shouldn't be there. Oh, but that's okay because I can just factor that out. After all, this is a linear operation. Integration is a linear operation. So I can write this as 12 times the integral of 1 over 1 plus 9x squared dx. Or, even more telling, we can write this as 12 times the integral of 1 over 1 squared plus 3x quantity squared dx. And now there's really no question. 1 over constant squared plus something with a variable squared. Oh, that's definitely that. So when we integrate something like that, we're going to take 1 over a times the arctangent of u over a. Okay, so that's going to give us 1 over a, that's just the number 1, times the arctangent of u, which in this case is that 3x, over, again, a, that's the number 1. Don't forget that whole thing's being multiplied by 12. And since you're integrating, we get a constant of integration. So in the end, our answer is going to be 12. That's 1, so we don't worry about that. 12 arctangent of 3x plus some constant of integration. And that makes us happy. Let's take a look at the next example. Let's say I want to take the integral of 1 over, let's see here. No, actually, before I do that, let me go back. I believe I made a mistake here. So here, this is 1 over a squared plus u squared, which is correct. But right here, it's not just a squared plus u squared. We also have the derivative of u in the numerator. So that means here, if our u is anything other than just x, that's going to have a value in the numerator. That's the derivative of this. So I've made a mistake here. That shouldn't be the number 1. That should be the derivative of this, which is the number 3. okay, but if we're multiplying this by 3, that's going to be a different answer. Well, not if we divide by 3 on the outside. So here, what I want to do is I want to say, okay, let me go ahead and multiply this by 3. That way, if this is u, this is du, right? Well, actually, I suppose I should say this is du, the derivative of u times dx. Oh, but if this is being multiplied by 3, I need to divide by 3 on the outside to keep everything balanced. Here, these 3's would cancel out if I let them. But instead of letting them cancel out, 12 divided by 3 is the number 4. And so that's going to be 4 times the integral of u prime over a squared plus u squared. Oh, okay, so the integral of u prime over a squared plus u squared, that's going to be the arctangent of 3x over 1. Okay? This 12 over 4 reduced to 3, so this is 4 times the arctangent of 3x, not 12. My apologies. Let's just like that. So now, anyway, going back to this one here, let's see. We're going to take 1 over x square root of 1 minus the natural log of x quantity squared. Okay, so here, again, pattern recognition. I have a square root in the denominator and something outside of that square root. Okay, so that really looks like one of these. All right, I have a square root in the denominator, and there's something on the outside. Oh, but that's not quite right. Because notice right here, I have a constant minus a variable. But here, that's a variable minus a constant. The order is wrong. A subtraction is not commutative, so I can't just switch the order. Constant minus variable. Well, that's the only one that's constant minus variable. So it kind of looks like this one, but this one doesn't have anything on the outside. That does. So it kind of looks like this one, but not really, because it's missing something on the outside. It kind of looks like this one, but not really, because that's the wrong order. And it definitely doesn't look like that one, at least I don't think. So here, we're not really sure which one it is, at least not, it's not obvious in any way. So what we're going to do is we're going to try to simplify this. What we want to do is we want to say, okay, well, whatever it is, I know this is my u, right? Because it's variable being squared. Okay, so let's go ahead and try that. I'm going to set my u to equal to the natural log of x, because that's a variable function that is being squared. Okay, so if that's u, then du is going to equal to u prime dx. Speaking of which, I forgot my dx here, didn't I? There we go. It's going to be u prime dx. Okay, well, u prime is going to be the derivative of the natural log of x. And the derivative of the natural log of x is 1 over x. So it's 1 over x dx, like that. Oh, but that's what this is. Look, 1 over x dx. Oh, okay. So here, this isn't really there. I know that sounds a little strange. It's not really there. Well, of course it is. Look, it's right there. Well, yes, but when we perform our substitution, it isn't really part of the denominator. This entire thing, 1 over x dx, is simply going to become du. So here, that's going to be du. In the denominator, I have square root of 1 minus, I'm calling that u, which I am now squaring. Oh, okay, so now it's obvious. Du over constant squared, du over constant squared minus variable squared under a square root. Du over constant squared minus variable squared under a square root. That's got to be the arc sign. So that's going to be arc sign of u over a. Okay, so that's going to be arc sign of u over a. Notice here a is the number 1 because that's the number that gets squared. 1 squared is still 1. Plus a constant of integration. But of course, u is a stand-in for the natural log of x. So here we can write this as the arc sign of the natural log of x plus a constant of integration. We don't really need to divide by the number 1 there. And that's our antiderivative. Again, be careful when it comes to expressions that might be disguised a bit. Try this. Take the integral of 3 over 2 square root of x times 1 plus x dx. Notice this doesn't quite look like any of our expressions because, again, constant plus variable. We don't have any of those. We have constant squared plus variable squared, right? And then we have constant squared minus variable squared, and variable squared minus constant squared. This one has something outside the square root. Well, I'm not quite sure, right? So give that a try. Pause the video to give yourself as much time as you need and give this a try. You're going to be well served by using a substitution like we did here. Try to find some value for your value of u here. Say u is equal to something, and use that to find du, and then try to rewrite your problem in a way that looks like one of these three expressions. All right? So go ahead and pause the video, give it a try, and whenever you are done, unpause and we'll go through that one together. All right, so this one looks like, well, there's nothing I can do, right? There's nothing, this doesn't fit this kind of formula. It doesn't fit this kind of integral because I'm supposed to have a constant squared plus a variable squared. Well, okay, well, that's a constant squared. 1 squared is still 1. But here, there's no square. Well, sure there is. After all, everything is squared as long as you start with its square root. Here, we can say, well, let's let u equal to the square root of x. That sounds like we're cheating a little, but that's perfectly valid. If u is equal to the square root of x, then squaring both sides, that u squared is now the square root of x squared. In other words, x. So here, this is 1 squared plus u squared. Okay. If you had an answer before, I'm going to go ahead and keep going here. But if you didn't, you might want to pause the video again and use that information and see if you can't get to the end of it now. Okay, so we're going to go ahead and say u is equal to the square root of x. Okay, so then du is equal to u prime dx. That's how we define a differential. All right, well, the derivative of u is going to be the derivative of the square root of x, which is going to be 1 over 2 root x dx. And notice that's what this is. Here I'm going to say 3 times 1 just to make it a little bit more apparent. That's 1 over 2 root x dx. This whole thing that I've circled is du. You say, what about the 3? Well, that's just a constant. You can pull that out. So here we can write that as 3 times the integral. All of this stuff is just your du over 1 plus, remember, x is the same as saying u squared. Just like that. So now, it becomes apparent, it's going to be this one, arctangent. So du over constant squared plus u squared. Du over constant squared plus u squared. Oh, well, here the constant's got to be 1. So that's going to give us 3 times 1 over that constant that's being squared. 1 squared is 1. Times the arctangent of u over that constant that's being squared, which again is the number 1. And then the whole thing is, you're going to add a constant of integration. To the whole thing, you're going to add a constant of integration. Keep in mind, u is a stand-in for the square root of x. So this whole thing is 3 times the arctangent of the square root of x plus some constant of integration. Okay. Did you get that? Okay. If you did, well done. And if not, try to find the mistake. Try to see where you went wrong and learn from that mistake. Now for our next example, we're going to see one which it does fit this category, but it's going to look like it doesn't, very much so, until we rewrite it. So let's see here. Let me turn on the light. It's getting dark in here. So let's try, there we go, that's a little better. Yeah, everything looks a little clearer now. Oh, now I got the shadow going. Oh well. Let's see, example. Let's go and try this one. I'm going to take the integral of dx over x squared plus, and you say, oh, okay, well, that's going to be an arctangent because obviously it's variable squared plus constant squared. Well, not quite. I'm going to have this. That's that's x squared plus 4x plus 8, which definitely is not a constant squared plus a variable squared. That's a variable squared, sure, and that's a constant squared. And you say 8 is not the square of a number. Sure it is. It's the square of the square root of 8. Technically, every number is a square, as long as you're willing to deal with irrational numbers. Right? 5 is square root of 5 squared. 8 is square root of 8 squared. But that still doesn't help us with this. None of our expressions have something that's going to help us with that expression. Right? Well, no, there's nothing calculus can do about this. But there's plenty algebra can do about this. Let's remind ourselves of a technique that we've seen all the way back in college algebra. It helped us to find the centers of circles and the vertex of parabolas, and that was the process of completing the square. So we're going to take this denominator, and instead of having it as x squared plus 4x plus 8, we're going to rewrite it so that it is a constant squared plus a variable squared. Completing the square works like this. We're going to take the first two terms and we're going to bunch them together. This is something that you've seen all the way back in college algebra, so if you remember how to do it, well, you can fast forward through this part of the video, right? If not, well then we're about to review how to do it. Take the first two terms and bunch them together, put them in parentheses, leave a little space because we're going to fill in a gap right here in a moment, and then leave the constant on the outside. Okay. The next step is, if whatever number is right here, you're going to factor it out. In this case, the number is 1, so it's not really going to make any difference. But here, let me actually write it outside just to highlight the fact that that's what we would do. If, for example, if this was the number 2, I would factor out the number 2 here, and then all of these numbers would change. All right, since I factored out the number 2. So factor out whatever number is there. In this case, since it's the number 1, it's not actually going to change anything when you factor it out. Okay. All right, now comes the part that completes the square. You're going to take whatever number is there, you're going to cut it in half, so half of 4 is 2, and then you're going to square. So take half of 4 is 2, then square the 2. Okay, well then that's a 4. That's plus 4 right there. But we just added a 4. Well, that changes the problem. That's not the same problem we had before. Okay, so let's balance that out by subtracting 4. Notice that this expression is now a perfect square. You can write this as x plus 2 quantity squared. You're factoring it. 8 minus 4 is just a positive 4. And so now this expression over here can be written as x plus 2 squared plus 4. Hey, look, variable expression squared plus constant squared. Now I can use the results that I had from my theorem. Here, let me rewrite this ever so slightly just to make it look even more like what I'm used to in my theorem. I'm going to write this as dx over 2 squared, that would give me my 4, plus x plus 2 squared. You don't have to rewrite it this way. You could go from here. But here, I've rewritten it this way to highlight even more the similarities between that and this right here. I have my differential over a constant squared plus a variable expression squared. Just like that. All right, so here we go. So here, the expression is simple enough. I can just go through and get the answer now. But just to compare it with the problems we've been doing, let's go ahead and use the substitution. Here I'm going to let u equal to that x plus 2, which means du is going to be u prime dx. The derivative of u is going to be the derivative of x, which is 1, and then the derivative of that constant is 0. So 1 plus 0 is 1 dx. Oh yeah, well that's that thing right there. Okay, so here we can write that as du. Notice du is dx in every way, shape, and form right there. Over 2 squared plus, that's the thing we're calling u squared. And now from our theorem, we get that that's going to be 1 over a times the arctangent of u over a. Okay, so that's going to be 1 over, that's your a, times the arctangent. Tangent has 3 letters, and I still managed to misspell it. And I managed to misspell it again. How did I do that? There we go. The arctangent of u over a plus your constant of integration. And of course, u is a stand-in for that thing right there. So we can write that as 1/2 times the arctangent. Yeah, I got it. Arctangent of x plus 2 over 2 plus your constant of integration. And that's your result, which makes us happy. So here, give this a try. Same kind of problem. Go ahead and find the integral of, you're going to have to complete the square just like we did in the previous one. Go ahead and find the integral of dx over 3x squared minus 6x plus 12. All right, you're going to do it just the same way we did up here by completing the square. Go ahead and pause the video, give yourself as much time as you need, and once you're done, go ahead and unpause and we'll go through this one together. All right, so let's go ahead and complete the square on this one. If we take 3x squared minus 6x plus 12, we're going to take the first two terms and bunch them together. So 3x squared minus 6x. I'll leave some space in there and leave the 12 on the outside. I'm going to take my lead coefficient and factor it out. All right, since I'm factoring out the number 3, that's going to leave me x squared. And here, if I factor out the number 3, that's going to leave me minus 2x. Notice, 3x squared minus 6x. That still says the same thing, even though it says it in a different way. 3x squared minus 6x plus 12. All right, so now we can complete the square by taking this, cutting it in half, which is -1, and then we're going to square it, which is a +1. Half, then square. But here we just added something, so we've changed our problem. Notice this is 3x squared minus 6x plus 3 plus 12. Plus 3. There's not supposed to be a plus 3. There was never a plus 3 before. Okay, so let's subtract 3 to balance that out. Notice up here we use the exact same number, and over here we didn't. What's the difference? 1 times 4 is 4. So you subtract 4 to balance that out. 3 times 1 is 3. So you subtract 3 to balance that out. All right? If you multiply all this out and combine like terms, you will still get 3x squared minus 6x. These two cancel out, plus 12. That now factors down. So this is 3 times x minus 1 squared. And then subtracting these is going to give me plus 9. Just like that. So I can now write this as the integral of dx over 3 times x minus 1 squared plus 9. And now I'm going to write this just like I did above. Yeah, that is perfectly fine, but I'm going to rewrite it this way so that it's constant squared plus variable expression squared. So that's dx in my numerator. So integral of dx over, what do I square to get 9? Well, I square a 3. So that's going to be 3 squared. What do I square to get all of this? Well, I have to square x minus 1 to get x minus 1 squared. But then I also have to square something to get 3. Well, that's going to be the square root of 3. All right. If you square the square root of 3, you get just 3. If you square x minus 1, well, you get x minus 1 squared. And then plus squaring 3 will give you 9. All right, so now this is dx over a squared plus u squared. Okay, so let's go ahead and make sure that we have the correct constants. Let's use the substitution. So just like above, I'm going to find something and call it u. And here the choice is obvious. It's whatever variable expression is being squared. Oh, well, that's the only variable that's got a square on it. So let's let u equal to the square root of 3 x. Here I'm actually going to distribute it. Root 3 times x, and then minus root 3 times 1. So just like that. Which means du is going to be u prime dx. The derivative of root 3x is just root 3. And the derivative of that constant is just 0. So let me not worry about that. That's just going to be root 3 dx. Just like that. Okay, so there we go. Du is equal to root 3 dx. Notice I don't have a root 3 dx. I just have regular dx. Okay, so I really should be getting rid of that root 3. I don't need it. Okay, so let me divide on both sides by root 3. Let me divide on both sides by root 3. Like that. These divide away, and I'm left with a simpler expression of dx is equal to 1 over root 3 du. Okay, that's that dx right there. Okay, so now we're ready to go. This is going to be the integral of that dx is 1 over root 3 du. Notice 1 over root 3, that's constant, so I can just pull that all the way out. That du I'm going to leave inside. Over 3 squared. And remember, that whole thing is what you're calling u. So we'll call that plus u squared. And now we're good to go. That's an arctangent function. So it's going to be 1 over root 3, that's that number outside, times, whenever we take the integral of something like du over a squared plus u squared, we saw in our theorem, that's 1 over a times the arctangent of u over a. Okay, so 1 over a times the arctangent of u over a plus a constant of integration. Now, of course, we know that u is a stand-in for all that stuff right there. Okay? So here we can write this as 1 over 3 root 3 times the arctangent of all of this stuff over 3. Or if you left it as root 3 times x minus 1 in parentheses, that's also fine. Over 3 plus our constant of integration. And I guess here I can rationalize that denominator. So that's going to be root 3 over, let's see, that's 3 times 3, that's 9, times the arctangent of square root of 3x minus the square root of 3 over 3 plus a constant of integration. So that gives us our result, which makes us happy. All right. Okay, so let's leave that there for a second. Okay. Every once in a while, we're going to run across a problem where the substitution, as we've seen already a few examples, choose u and such. For the most part, the choice of substitution is something fairly obvious. It's, well, there's one variable here. There's one variable expression here, so that's probably what I want to choose for u. Same thing for this one. Once I've completed the square, there's one variable expression, and that's probably what I want to choose as the value of u. However, you'll also see some problems where it's not anywhere near as obvious. So let's take a look at one more example that looks something like that. Oh, let's see here. Let's take the integral of the square root of x minus 2 over x plus 1 dx. Now, this is going to require a technique that you first learn in Calculus 1, In our current textbook, it's at the end of chapter 4, and that's called change of variables. In this case, we're going to note that if we try to integrate with any technique that we currently know, using a logarithm, an exponential, or using any of our current, using any of our current trigonometric functions or inverse trigonometric functions, you're not really going to get anything from this. So instead what we're going to do is we're going to try to rewrite this expression by changing the focus of it. Here we're going to take part of the expression and change the expression to be written in terms of that one part. Sometimes it's hard to know which part it's going to be. In the current homework, you'll be given some problems where you're going to have problems where change of variables are necessary, and they're going to do you the favor of actually telling you which ones are which part of the expression you want to focus on. If that's not given, sometimes you just have to try it out. Here, I see a few options. I could say, okay, let me take x minus 2 and call it u. Or maybe I want to take the square root of x minus 2 and call it u. Or maybe I want to take x plus 1 and call it u. All right? I don't have too many options. So here, the one I'm going to use is, I've gone ahead and done the problem ahead of time, so I know which one to use. That way I don't waste your time showing you a couple of other ones which might not work. Here, I'm going to go ahead and perform the substitution. I'm going to say let u equal to the square root of x minus 2. So I'm taking the entire numerator and calling that u. Okay, well if that whole thing is u, then that means du is going to be u prime dx. That's the definition of du, the definition of the differential of u. All right, well the derivative of this, the derivative of the square root of something is 1 over 2 root of that something. That's something we do to death in Cal 1. The derivative of the square root of something is 1 over 2 root of that something. Now the chain rule tells us to take the derivative of the inside, but the derivative of x minus 2 is just 1. So here I guess you could say times 1, but it won't really do anything. So it looks like that. Okay, so now if u is equal to the square root of x minus 2, all right, that's fine for the numerator. But notice the denominator doesn't involve square roots at all. I don't want to involve a square root. That's going to make this inaccessible. Okay, well, let's get rid of the square root. If we say u is equal to the square root of x minus 2, well, then we can just write this as u squared is equal to x minus 2, like that. Square both sides. And if I take this expression down here, du is equal to 1 over 2 root x minus 2 dx. Notice that that expression right there is u. Okay, so what? Well, look, if I say du is equal to 1 over 2 root x minus 2 dx, I could multiply right here by 2 root x minus 2, and that will get rid of that. Now over here, I shouldn't multiply by anything that involves an x, right? Here, this expression involves the substitution, u. I don't want to have x anymore. Well, yeah, but look, 2 doesn't involve x at all. It's a constant. Okay, so I can use 2 on both sides. Oh, but I can't use square root of x minus 2. Well, that's true. But the square root of x minus 2 is u. So here, multiplying by 2 square root of x minus 2 is the same as multiplying by 2 times u. These are now gone, and I'm left with the expression dx. That's the only thing left on this side, is equal to 2u du. So now from here, we'll be able to rewrite our expression in a more useful way. Note that our numerator is just u now. That is just u. Okay. X right here. Well, look right here. If we have x minus 2, that's equal to u squared. Okay, so if I just add 2 to both sides, that means x is equal to u squared plus 2. So that x, I can replace it with u squared plus 2. That x, I can replace with u squared plus 2. But now there's an extra plus 1 right there. And then don't forget your differential. dx is replaced by 2u du in this new substitution, in this change of variables. So let's rewrite that just a bit. We can write this as the integral of, let's see, 2u times another u, that's 2u squared, over, the denominator is u squared plus 3 du. Like that. That 2 is a constant. We just factor that out. So we can write that as 2 integral of u squared over u squared plus 3 du. And now, by our change of variables, we have a much simpler expression. Note right here, the numerator and the denominator have the same power. Whenever you have a numerator and denominator with the same power, you can divide first. In fact, you should divide first because that'll simplify the expression in a way that makes it a lot easier to work with, other than what we have here. There's two ways you can do it. One is you can actually use long division. You can say u squared divided by u squared plus 3 and actually get a result. Let me show you a different way to do that. That's much, much simpler. Notice right here, this is almost the same as the denominator. Well, yeah, but it's not. But if it were, that'd be great, right? Because u squared plus 3 over u squared plus 3 is just the number 1. Okay, well, let's make it the same. Let's just add 3 to the top. Great, now everything cancels out. Yeah, but you can't just add 3. That changes the problem. Well, okay, let me balance that out by subtracting 3. Okay, well, if these cancel out, that nothing really happened. So what was the point of doing that? I can now split this. I can write this as u squared plus 3 over u squared plus 3 minus 3 over u squared plus 3 du. Most people would do that step in their head, but you can't see it in my head, so I'm going to write it out. Notice u squared plus 3 minus 3 over the same denominator. This is exactly what the previous line said, but now that's just the number 1. So here you can write this as 2 times the integral of 1 minus 3 over u squared plus 3 du. It's much simpler than dividing, at least I think. This is a trick that comes in handy fairly often. In fact, you've seen it already in this section. Adding and subtracting something to rewrite expressions in a way that's convenient. That's a trick that appears all over in calculus. In this case, we can use that to divide things efficiently. In any event, we can now integrate. Hey, look, the integral of 1 du, here, let me even write it as two separate things. That's going to be 2 times the integral of 1 du minus, here that 3 is a constant, I can factor it out, the integral of 1 over u squared plus 3 du. 2 times that whole thing, which is the integral of 1 du minus the integral of, that 3 can come out, 1 over u squared plus 3. And now each of those integrals I know how to do. That's 2. The integral of 1 du, that's just u, minus 3 times, that's an arctangent. All right? Here, that's simply going to be 1 over, here, if this is a squared, then a is just the square root of 3. All right? What number do you square to get 3? You square the square root of 3. Okay, so over here, I'm going to have that as 1 over a, arctangent of u over a. 1 over root 3 times arctangent of u over root 3. Plus some constant of integration. Keep in mind, u, well here, let me simplify first. So I can write that as 2u, 2 times u, minus 6 over root 3 times the arctangent of u over root 3 plus a constant of integration. Gone ahead and distributed that 2 throughout and multiplied those together. Note that I can rationalize those denominators. Let me multiply by root 3 top and bottom. So this will give us 2u minus, here that's going to be root 3 times root 3 is just the number 3. 6 divided by 3 is 2. So this right here gives me 2, and then I have an extra square root of 3 there. So 2 root 3 times the arctangent of root 3 times u over just the number 3. Root 3 times u over the number 3, plus a constant of integration. And finally, we're almost done. Note that u is not the variable that we started with. Our original function was in terms of x. Well, yeah, but u is just a stand-in. U really means the square root of x minus 2. Okay, so we can do that. So this is going to plug that back in. That's going to be 2 times, instead of u, I'm going to have the square root of x minus 2. That's a big square root sign. Minus 2 square root of 3 times the arctangent of the square root of 3 times the square root of x minus 2 over 3 plus a constant of integration. And notice, since this is the product of square roots, I can just merge those together. So in the end, I get a result of 2 square root of x minus 2 minus 2 root 3 times the arctangent of the square root of 3x minus 6 over 3 plus a constant of integration. Oops. And that right there denotes my final answer, which makes us happy. And that brings us to the end of our section. We've seen how we can integrate things of either this form, or this form using the arc function, the arcsine, arctangent, and arcsecant. We proved one of them. You'll see another one in your homework. And we've seen some examples on how to do that. First of all, we saw the more obvious ones where they just look correct. They look like the correct form. Then we saw some where we had to do a little bit of work, either through substitution, where we have to find the right expression to substitute for u, or through completing the square. And finally, we saw an example where your substitution may not be obvious. When the substitution is not obvious, we have to try a few different things. This technique is something you learned in Cal 1 called the change of variables. And that's at the end of chapter 4 in your current textbook. Change of variables. Because you literally change your integral from being variables of x to variables of u. And then when you integrate, you change back to the variable of x. So that's it. If anybody has any questions, comments, or problems, make a note of those and let me know during our next meeting or during our next office hours. And I hope everyone has a nice day.